dipolar field. So let's just say this is in the outer core. Convection drives the Earth's magnetic field, and this is a relatively thick layer. So we call this a thick shell dynamo as a result. So that's just language. And the point is, it's possible if the material to have iron and rocks mix, but the temperatures are extremely high. So Sean Wall worked this out in 2015, and it's possible to have this layering not occur, but the temperatures have to be very high for that. So in general, keep in mind, anything that is immiscible at modest temperatures becomes miscible at high temperatures. So that's important at some point. So for this talk, it's also important under what conditions does iron crystallize. So we think these planets formed hot, then they cooled and crystallization started. And Dario Alfei published an important paper in 2000, and Felipe Gonzalez extended this work to much higher pressures and computed the melting line of pure iron. So that's important because if you look at the interior temperature structure of our planet, you know that the Earth core could not be arbitrarily hot, because otherwise there would be no inner core today, and we know that it exists. So someone came along and says the Earth inner core has a temperature of 10,000 Kelvin. You can say, no, this is impossible because it would be too hot for an inner core to crystallize based on lab experiments and on computer simulations. So you think at these conditions here for the inner core outer core boundary, it's around 6,000 degrees Kelvin. So you have some constraints. The melting line of iron constrains the inner core temperature as a result. So if you look a little bit further out in the solar system, you find Jupiter, for example. It has a gigantic magnetic field, the strongest besides the sun in the solar system. And here's the Juno spacecraft as it flies through this intense sort of radiation belt, because there are many charged particles are trapped in this field. Whenever you fly through, then the spacecraft is exposed to intense harming radiation. So you have to harden your spacecraft appropriately, and that can be a challenge at times. But nevertheless, this Juno spacecraft is healthy, and it measured the gravity field with high precision. And the way this works is Jupiter is a rapidly rotating object. As a result, you have a centrifugal force, and the planet's shape is deformed and mass is redistributed. It's not a point mass, it's an extended mass, and that deforms the gravity field. And we expand this in a series of Legendre polynomial. And the first term is J2, and that measures the overall oblateness and just given to the centrifugal force. And that's the correction to the 1/r potential that we get for a point mass. And then Jupiter's shape is not a perfect J2 object. They're J4, 6, and 8, and they all lead to contributions for the gravity field. And these coefficients have all been measured with very high precision, because we have an orbiting spacecraft that comes by at close range and makes repeated measurements. And the J2 is known to very, very high precision, and the other ones as well, as you can see here. This is much, much better than we knew before when we only had a flyby mission, where you just have one measurement, and that allows us to measure J2 and J4, but J6 was unknown. And if you now look to Uranus and Neptune, then we have only flyby measurements from Pioneer and Voyager 2, and therefore these J coefficients are not that well known with high precision. But for the future mission to Uranus, we will measure them with about a factor of 1,000 higher precision once we have an orbiting mission around Uranus. So this is for the future. This is not something we'll get tomorrow. So if you look at models that have been constructed for Uranus, for Jupiter and Saturn, as we've shown here on the left and right, we think the magnetic field is generated in a thick layer of metallic hydrogen, and it makes gigantic dipolar fields. But all of models that are constructed today, they have a layer of helium rain. And the result of helium rain is because hydrogen becomes metallic, while helium does not. and the electronic structure of something that's metallic and something that's not, that renders these interactions unfavorable. And as a result, helium will rain out. They become immiscible. So all models currently accepted this, and it's driven. This theory was developed by Stevenson and Salpeter, and they started with one key measurement. They basically looked at the radiation that was emitted by Saturn and says, hey, this is much more than a gradually cooling planet should emit. We call this the excess in Saturn's luminosity. And Stevenson and Salpeter said, how we can explain this? And the upshot was, well, we only have hydrogen and helium to play with. That's the major components of Jupiter and Saturn. What could be the origin of this excess thermal emission? And they basically said, if helium becomes immiscible, it rains out, it releases gravitational energy, and that could be this energy source that leads to this thermal radiation that would otherwise not be present in this quantity for a gradually cooling planet. And that has now been confirmed with computer simulations and also with lab experiments. But the key measurement was this thermal radiation that led to this theory a long time ago for the immiscibility of hydrogen and helium. So we have one measurement led by Stéphanie Brigou and Paul Loubert and Rip Collins and others who basically measured this in the lab. And they confirmed the presence where theory had predicted is around 1.5 megabars, but the temperature measurements are results differ very much from the theory. So in the theory, we think this occurs around 5, 6, 7,000 Kelvin, but the measurements predict something like 10,000 or 11,000. So this is a big conundrum. We don't know how to fix this. This talk will not address it. The state of the art is, yes, hydrogen and helium become immiscible at 1.5 megabars, but the theory in this experiment disagrees on the temperature. So I want to just say from a theoretical point of view, I will follow this immiscibility calculation by Miguel Morales. And I want to then extend this work to Uranus and Neptune, not for hydrogen and helium, by other materials. But in general, what you need to know is planets cool through convection, because thermal radiation cannot get through, and thermal diffusion is inefficient. That leaves a convecting planet, as you just seen here. If you don't know what convection is, order miso soup in a restaurant. Ron, we've been there many times. These little particles in the miso soup are the best way to actually observe the radiation, the convection directly. That's my recommendation, to familiarize with the process of thermal convection, because it's always served hot and it's cooled from the top. So that needs, in a planet that's very hot, where everything is miscible, everything is on an adiabat, a curve of constant entropy. So as the planet then cools, it may enter an immiscibility region, where you then have a layer where the planet can no longer convect through, and that's what we're predicting for Uranus and for Jupiter and Saturn. And then there's a layer here where in this immiscibility region that is presumably not convecting and stably stratified. And the way these adiabats work out is that there is a lower layer where it's then convecting again, but in this layer where it's immiscible, helium will rain out. And there is now good theoretical evidence to at least make this compatible with the excess in luminosity for Saturn. So we are working a little bit on these calculations. What you need to know is you calculate Gibbs free energies as a function of composition. And then you should typically subtract the result from the end members to make this a little bit easier to see. At high temperature, this curve is always convex, and therefore it's completely miscible in all proportions. But if you go to lower temperatures, then you develop this immiscibility gap, where you're somewhere in the middle. You have a composition, then the system can lower its energy by forming helium droplets of helium rich. They're here. And you do a common tangent construction to determine what's the remaining material that's then hydrogen rich. And therefore, you start in composition like here in the middle, you form these two sort of phases, and one is helium-rich and the other one is hydrogen-rich, and then the heavier phase will roll out. And this all has to happen inside conditions, pressure and temperatures, for so that matches the temperature and pressures in a planet. So if you predict something, it has to be at the right conditions, and therefore for making a fully consistent planet. So this is a thermodynamic calculations based on Gibbs free energies, and it tells us something is immiscible if it has this particular Gibbs free energy curve, where the system can lower its overall Gibbs free energy by phase separate. So we do these calculations like many others using density functional theory, which is not a perfect theory, but it gives you a relatively reliable answer for modest investment of computer time. So if you want to do a better theory like quantum Monte Carlo, then it becomes 100 times more expensive. So as a result, we use this relatively simple theory because we run many simulations between 100 and 500 atoms. And then we run molecular dynamics where we have to repeatedly calculate those forces. So this is sort of the working machinery, and many people in your center can do these calculations, and we can do that too. So on the left, what we do is this little trick to calculate free energies. A standard molecular dynamics calculation will only give you pressure and internal energy, but not calculate an entropy directly, and therefore you do not have access to a Gibbs free energy, which is important for these immiscibility calculations. What we do is we do for constant volume and temperature simulations, we do an adiabatic switching method, which we call thermodynamic integration, and that allows us to calculate differences in free energies, and also then gives us access to the entropy and gives us access to the Gibbs free energy. This goes all into this. So what we do is we run DFT, gradually switch to classical forces that we construct, and then we do another thermodynamic integration for these classical forces to calculate the free energy of that classical system. So there's a little bit of a machinery involved, but we think this is the most reliable Gibbs free energy calculation method we have within density functional theory. So this classical system, we do a little bit of work to construct this. This gives us a Gibbs free energy based on the DFT forces. There is another way. You can actually infer phase separation. So if you're deep inside where the system will actually not want to mix, and we've done this here on the right for hydrogen, helium, you look at where are the helium atoms, and they're not homogeneously distributed. They're not forming a perfect bubble, but they're concentrating near each other. So there is, if you're deep inside the immiscibility region, the system will spontaneously phase separate. You don't do any calculation that involves Gibbs free energies, just look at the system. And then if you calculate these pair correlation functions that measures for a helium atom, where are my other helium atoms? Then it drops below 1. So normally these functions normalize, it goes to 1 at large distances for a homogeneously mixed system. But if it's not homogeneously mixed, then the helium atom sitting in the center will see many of his friends on nearby. But far away, there are not so many friends. So therefore, this drops below 1. So if you see a pair correlation function that drops below 1 at large distances, then you can tell the system is no longer homogeneously mixed. And this is just one example. So this is simpler phase separation spontaneously observed. Fine. So therefore, we have two ways to do that. On the right here, we do a thermodynamic Gibbs free energy calculations and calculate Gibbs free energies to infer a phase separation. And on the left, we have this dynamic simulation approach where we just see it, we just look at it, and there's heat until it mixes, heat until it melts, two-phase methods, or spontaneous phase separation. You want to do that. So this is much, much simpler. On the right is a little bit more technically involved. Importantly, if you want to do Gibbs free energy calculations, you have to know beforehand what phases are present. So if you don't know that, you can calculate all Gibbs free energies that you want. If you have the wrong assumption for a specific phase, you will never get sensible results. But in the left here, you have to be really overdriving the system into this new state, but at least you have to make few assumptions what that new state will be. So they have these two alternative approaches. Fine. So this talk is about Uranus and Neptune, and Uranus is far out in the solar system. It's 80 some years in orbit. It spins every 17 hours. It has 4 Earth masses. So it's one of those interesting regimes where we find many exoplanets now. It has a density that's a little bit heavier than water. So there's a water layer, presumably, and some rocks in between. That's a reasonable way to do that. It gives off thermal infrared radiation. But it's observable, but it's not very much. That's something we still need to understand. These planets are blue because there's a little bit of methane in the atmosphere. So if you wanted to go to Neptune, then it's a little bit more massive. It's 17 Earth masses. The radius is surprisingly a little bit smaller, and therefore the density is 1.8 times that of water, and therefore we think the rock fraction may just be a little higher. It orbits at a distance of 30 astronomical units, and it takes about 130 years. Overall, however, these are 2 ice giants, because we think they formed outside the ice line in the solar system. There was a lot of ice present, and as a result, it was incorporated into these planets. They didn't get much hydrogen because when they formed, most hydrogen and helium was either in Jupiter or in Saturn, but they got a little bit, but not enough to make metallic hydrogen, we think. If you compare the 2 planets, there are few things that stand out. So Uranus has been tilted on its side, and it presumably occurred because of a giant impact. That's still the leading hypothesis, even though you can tilt planets with spin-orbit resonances. Uranus has almost no intrinsic heat flux. We're not sure why that is. This talk will not address it. Uranus has a regular set of moons, and Neptune only has 2, and Triton is a gigantic moon. The interior structure is still highly uncertain. So we're allowed to make stuff up as theorists. And then this talk will focus on why is there such an unusual non-dipolar magnetic field. There are many papers recently that have tried to address one or the other aspect of these discrepancies between Uranus and Neptune. I do not have time to go through these papers. I want to flash them out here since this is recorded that other people can look at. It started early on, before Uranus, before Voyager 2 arrived. A famous person in the field predicted that these planets only have a very small field that's generated at the center of the planet, and it should be spin axis symmetrized. And that turned out to not be confirmed. What was actually found was that these planets don't have strong dipolar fields, but they're fields, but they're not dipolar. And people really wonder, why would that be? And there were 2 hypotheses. One would be saying, well, maybe just we arrived when just Uranus was flipping its field, was during one of those reversals, but the chance is about 1%. Or the alternative would be that the fields of Uranus and Neptune are very different from that of Earth. So the answer, which one was correct, was given when it flew by Neptune, and then Neptune's field was also not dipolar. And that was clear. There was no chance it will be arrived during 2 reversals. The result is they have magnetic fields that differ very much from that of Earth, Jupiter, and Saturn. So something in these planets is just very different. So the first explanation for this was actually given by 2 Russian scientists, Wismaikin and Starchenko. And without computer simulations, they said you can get a non-dipolar field if it's generated in a thin shell. So that was new in the dynamo community. That paper here did not generate a lot of traction. I would say the authors also didn't become very famous as a result. Famous became actually Sabine Stanley and Jeremy Bloxham. In 2004, they published in Science an explanation based on the same hypothesis. They did dynamo simulations. And they could show with dynamo simulations that you get a field that resembles, broadly speaking, Uranus and Neptune, shown here. This is a non-dipolar field. And then Earth has a happy dipole with the North and the South Pole. And their computer simulations resembled features of these non-dipolar fields. And what you typically plot is you look at the power that is normalized by the dipole power. And for Neptune, for example, there is more power in the quadrupolar or octopolar field compared to the dipole. So it's very different from Earth, where the degree 2 field is much weaker than the dipolar field. And their simulations at least sort of got close to this. So what they basically assumed is there's a thin shell where the field is being generated in the outer 1/3, and that is contrasted to a thick shell dynamo where the outer 2/3 make the field. But here, if you just have a convecting fluid in the outer 1/3, you do get these non-dipolar fields. So Sabine Stanley and Jeremy Bloxham in their 2004 and 2006 papers made a number of predictions. And they basically said it's generally the field's generated in this outer layer and not below. And the field in the outer layer is generated by a homogeneous electrically conducting fluid that convects. The radius boundary is probably put approximately at 2/3, but this is not a fixed number, but it shouldn't be as small as 1/3 they predicted. And in the inner layer, they proposed it should also be a fluid. That was the best way to reproduce these fields in the dynamo simulations. And a stably stratified electrically conducting fluid was preferred in these publications. And if you basically say, well, it could also be a solid as an alternative, but then they already said that the simulations wouldn't match the observations that much. What both authors could not address is what's the composition of the upper layer? What's the composition of the lower layer? And most importantly, why wouldn't the lower layer convect and contribute to a magnetic field? Presumably, you have two convecting layers, then the convect would be a fine sort of combined. There would be an ordering force, and you get a giant dipole field. The way I think about it is a dipole field emerges if the magnetic interactions leads to ordering of the field. So if you have a very thin layer, then the ordering force is very strong. And then you're left with these not so very well ordered fields. But if you have a thick layer, then you presumably make a dipolar field under many conditions. So this talk will address these open questions, and we'll come back to this. So this is the work by Sabine Stanley and Jeremy Bloxham. Since then, other people have constructed alternate scenarios. For example, there is the work by Krista Soderlund with Jonathan Arnault, and there's also Hao Kao and Paula Wolf. They're all working on alternative explanations why Uranus and Neptune's field are not dipolar. But in this talk, I will focus on this work by Stanley and Bloxham, saying that we have two layers and the lower one is not convecting. But the dynamic community has not completely settled this, and there are people working on this, whether there's another space of solutions. We will follow this early work here, and we try to come up with an explanation what it could be a possible composition. So we know that there is methane on these planets. It's about 80 times enriched compared to solar. And there are other enrichments we've seen for Saturn and for Jupiter. This is not so unusual. So methane is present. And that led Marvin Ross to predict there is diamond rain of these planets. An influential early paper done in Livermore. And they asked the question about diamonds in the sky. So I had many conversations with Marvin and Ross, mostly about the equation state of hydrogen, but I never really asked him how he came up with the title for this paper that now has been so influential. But he predicted if you have CH4, put it at high pressure, you pyrolyze it. So you make diamonds and the hydrogen comes up. This has been seen in experiment. Here's Robin Benedetti. She laser heated methane and she see the formation of diamond in situ. There are computer simulations by Sebastian Hamel combined with experiments by Ricky Chow and Bill Nellis, and they see that you have a polymeric state that is produced under these extreme conditions. So that's one scenario. Our paper came out a year later. We did methane simulations led by Benjamin Sherman, who was a summer student, but already at Berkeley at the time. And he published this very important paper. So if you are a summer student, you can actually publish papers that later on become very important. And in his simulations, Ben actually showed the longer you run them, the more polymers you produce. And also the higher the pressure, the more polymers produce. So you think about it. And you assume this might be happening in Uranus and Neptune. This is an important fact to infer. If you make polymers, then hydrogen can bubble up because every time you make a carbon-carbon bonds, you release hydrogen. So we proposed this to the NSF, and actually the NSF proposal was funded as quite some time ago. But it's important to come back what this means. If you think about from the planetary perspective, if this were to happen in the interior of Uranus and Neptune, and hydrogen will come up, and this is a process that is pressure driven, then it can lead to stable stratification. Because the deeper you are, the higher the pressure, the more hydrogen is released. So this is one mechanism to introduce a stable stratification in composition as hydrogen is released more at higher pressure. So keep this in mind. This is our sort of joker that we keep in our sleeve of our jacket just to play this card at the right moment. But keep in mind, if hydrogen is released, it's a way to stably stratify a fluid layer. What we proposed in our NSF proposal a while ago were 4 possible scenarios. One is basically have a homogeneous composition of ices, where we say water, methane, and ammonia. These are all planetary ices. They could all have been incorporated. And you have a planet here where you have a hydrogen layer with helium and a homogeneously iced layer on a rocky interior. Then we had a scenario B, where some of this hydrogen was released from this layer, a thick layer nevertheless. Then we have a way where you have a polymeric mixture. The hydrogen was released. You have a subionic water layer and a fully convecting water layer. This was our scenario C. And then in the other case, it's cold enough to make diamond. And you make another solid C3N4, which is the ultimate state if you remove all hydrogen and it's cold enough so it's not liquid. And that is our scenario 4, and all with the goal of explaining the Stanley Bloxham model of having a thin layer that makes the field. So that thin layer may presumably be water here, and there's something underneath that is not convecting. So that's the hydrogen is not participating in the field generation because it's not metallic under these conditions. But nevertheless, if you look at this one here, this should either resemble this layer or that layer. That's at least what was the goal. And the NF said they gave us money to fund it. And we started with this and we looked at the solid structures first. And yes, if you have diamond and carbon, a diamond and nitrogen, you make C3N4, and that is a convex hull diagram here that shows C3N4 is really a good solid to form at these conditions. That is ground state DFT calculations and showing that C3N4 is preferred. Then things did not go as expected, and we struggled with this because we did Gibbs free energy calculations for calculate the Gibbs free energy of this homogeneous ice mixture. And then we subtracted the Gibbs free energy from diamond, C3N4, from water and hydrogen. So for every single one, we did these thermodynamic integration calculations. We We calculated the Gibbs free energy of everything. We summed them all up of the phase-separated composition and the mixed composition. And here at 3000 Kelvin, we can say at about 2.5 megabars, the system will phase separate. That's cool. So we could say diamond forms at 2.5 megabars around 3000 Kelvin. That could explain why Uranus and Neptune have these two layers, because they separate. The problem is that the temperature for these conditions is approximately 5,000 Kelvin, not 3,000, but 5,000. And at 5,000, this phase separation is not preferred. So that was the result we got in 2015. We could never, ever get a calculation where the phase-separated system has a lower Gibbs free energy than the homogeneous mixed system at 5,000 Kelvin. Whenever we have a realistic temperature, the system that was fully mixed was always preferred. That was so annoying. Our thermodynamic calculations would not predict phase separation at the temperature conditions where we think the planet would be at. So we struggled with this. We could not solve the problem in 2015. We actually gave up. It was terrible. I wrote in the last NSF report, we could not solve this problem. So we questioned everything. We wondered, well, maybe there's some other way to make non-dipolar fields. Maybe all of those four scenarios are simply wrong. And we gave up, seriously, because we couldn't do it. By our own standards, we could not go ahead. If you looked at other people, what they've done, there's Dominic Krauss, 2017, he saw diamond formations with X-ray diffraction under shock conditions. Pretty cool. So they saw diamond here at very high temperatures, and that is one result that was produced once we were not working at this at the time. Here's a very comprehensive, maybe the best one, by Bingjing Cheng, Sebastian Hamel, and Mandy Betgenhagen. They looked at diamond at extreme conditions, and it's probably the best paper that's out there to look at conditions when diamonds will fall. We did some other things since we couldn't do the Uranus and Neptune probe per se. We looked at water and hydrogen mixtures, and we showed that, according to our computer simulations, that they mix under Uranus and Neptune conditions. So that's contradicted the two experiments by Barley et al. And but if you went to the last meeting, at the AGU meeting, we have some new results coming out. Kei Hirosei's group, they're very exciting. They seem to infer that these things are more miscible. So that might be now a new experiment that contradicts the Barley work that's more compatible with our computer simulations we published. We said under Uranus Neptune conditions, water and hydrogen are miscible, and therefore there's no sharp boundary between these two lengths. More recently, Kyla de Villa looked at compositions of the carbon, nitrogen, oxygen, hydrogen space, and she discovered a new state of matter, which we named double superionicity. And what she observed is that not only hydrogen goes superionic, but also nitrogen. While the oxygens, they remain in their lattice arrangements, the nitrogens eventually, if temperature's high enough, just below melting line, as you see here right now, they move like a fluid. So there are two atomic species that goes superionic or fluid at different temperatures, and that state had never been observed for a heavy nucleus, and therefore we labeled this double superionicity, and Kyla de Villa just received the AGU Jamieson Award for this work. Superionicity is an important in planetary science, we think, and that is all based on Cavazzoni's work. He worked at the project early on, and in 1999, he actually heated up water samples and showed there's this superionic phase where hydrogens move and oxygens do not. The group by Ronald Redmer actually revised, did many more calculations, and corrected the adiabats a little bit, and predicted that this is the state in the interior of Uranus and Neptune. So we looked at this a little bit, and at the time, everybody assumed that the arrangements in the oxygen nuclei was BCC, because that's what ICE-10 is. And we questioned this, we challenged, because there's so many other ICE phases have been predicted. And we showed that's preferred if the arrangement is actually an FCC arrangement. And that was published in Physical Review Letters and was then confirmed by Marius Millot with laser shock experiments. And he showed that there is an FCC arrangement of nuclei. And he also assumed that this work will explain the fields of Uranus and Neptune. And that's what I'm not sure I agree with him. And the result is that hydrogen will actually, the superionic water is actually a very soft material. It does not resist shear, so therefore it would convect and therefore not resist shear too much. So other results, Nadine Nettleman simulated, made models for planets in this arena. It's a very influential paper. There's also the recent work by the group of Peihao Huang, who said there could be H3O present. So this is all result of ground state calculations. They show that H3O may form at the pressure of about 450 GPa. That proposes that there's an H3O layer deep in the planet. If you're deep in the planet, things are also a little hot. So therefore, it's a little tricky to say whether this would be a fluid system or it would be a superionic H3O system. So this, nevertheless, is an interesting scenario. We did not know H3O existed. We, for some reason, didn't find it. We looked at a long, long time ago. We predicted H4O, that's Shuai Zhang's work, but we did not find H3O. It's wonderful, interesting work. So other people constructed layers in Ravid Hellet's group, having a hydrogen layer, an ice layer, and then a rock layer, and then looked whether these transitions are mixed or gradual. They also looked at the temperature distribution. Then I want to just move. Then in 2023, machine learning methods became popular. And then that was the reason for me just to revisit the problem. Or if you've not worked on this for almost 10 years, you said, how about we try again? Maybe something will work now, which didn't work the last time. So what I did is I took a system much bigger than I could simulate 10 years ago. And I started with simulations at quite high temperatures. So these are the Uranus and Neptune adiabat as predicted. And I'm right up here, and I simulated, and you have the oxygen atoms in red, you have carbon atoms in gray, nitrogen in blue, and hydrogen is white. And then we simulate approximately a solar abundance of heavy nuclei, and then we assume the hydrogen was delivered in these abundances. And then when I run these simulations, much bigger systems now, you get pretty much the same result I got 10 years ago, because they're homogeneously mixed. Oh, the equation state is not changing a whole lot when you switch from 100 to 500 atoms. However, then I lower the temperature to something that is much closer to the predicted Uranus and Neptune adiabats. And then I got one morning, I got this result. And that was just amazing, because at that moment I knew this is something that could explain the field, something I've never gotten before. This was a very exciting moment. If you look here, this is a simulation where I just removed the hydrogen atoms from the visualization to make the following effect a little bit easier to see. There is a layer that is predominantly oxygen-rich. And then there is another layer which is carbon-rich, and the nitrogen atoms actually remain predominantly with carbon. So this is an example where the computer simulations directly showed me, which I could not envision beforehand. It would show me phase separation at extreme conditions, like hydrogen, helium, but here we have the water-rich system, phase separating from carbon and nitrogen, and there's hydrogen in both of those things. We've never seen this before. This is very exciting because we have now the possibility to have a materials-based explanation why Uranus and Neptune do not have dipolar fields, and this is the remainder of the talk to flesh this out a little bit more. Whenever you get a new result, you have to make sure it's actually real. And real means to someone who has computer simulations, would someone reproduce this? So the first thing I did is I turned off all machine learning acceleration and confirmed these results. Because with machine learning, you can get a lot of funny results. You also have to make sure that they're actually compatible with the original DFT methods. I hope someone will do lab experiments to confirm this. And ultimately, a future mission engineers will hopefully infer the presence of these layers inside the planet with normal mode measurements. And I will conclude this talk that way. So what do we see is if you take these simulations and then you just look at the distribution of carbon and nitrogen, they form their own bubble where there's very little of it up here. So you see this bubble formation directly. Here's another way. If you remove hydrogen in from the simulation, you still find this effect. It's not sensitive to how much hydrogen is present. We looked at the pair correlation function. And if you look at carbon-carbon, you see this little dip below 1. So if the carbon atoms have all their friends nearby, then there are fewer friends far away. And this is this dip you see here. But we also have another signature of, and we look at the structure factor S of K, where you find it to go negative. If you have the structure factor, which you measure with X-ray diffraction, you look for the carbon-oxygen structure factor. It has a very peculiar shape. It goes negative at the longest wavelength that fit in your cell. And you ask yourself why that might be. The longest wavelength is just a vector that just fits in your box. And if there's a carbon and the nitrogen atoms far away, and you divide by L, then this cosine function becomes negative. So carbon and oxygen atoms far away will make negative contributions to this S of K functions that outweigh positive contributions from nearby. So if you see that one of those functions goes negative, that is another good indicator that phase separation has occurred. So we repeated these things at the hydrogen depleted simulations. We also see this go negative, or here show it as a function of time. That is a good indicator that phase separation has occurred. So at high temperature, we don't see it. So therefore, I think Uranus and Neptune cannot be very hot because this phase separation is a low temperature effect. And at high temperature, everything will mix. So I want to use the remaining time to talk about the implications for Uranus and Neptune a little bit, because we have actually done models for this. So we do everything with the concentric Maclaurin spheroid method. This is completely separate from the DFT calculations. We have certain parameters for these models, and we always go back to use the equation of state that we computed with DFT for given pressure, temperature, and composition. And then we do a full-fledged planet model, and we calculate the gravity field, and even compare it to the Voyager measurements. So the result of these things is a complete ensemble. I show you the final result. We're proposing for Uranus and Neptune. There's the outer hydrogen helium layer, has about 4% of the mass for Uranus. Then there is a thick layer of hydrogen and water. That's where the field is generated. And we have another layer below that now needs to be stably stratified. The layer is fluid and electrically conducting, but it cannot lead to large-scale convection because it has a varying hydrogen contents. So we assume for these models that phase separation is complete between water and the carbon-nitrogen system. You don't have to make this assumption, but you make these models, you have to start from somewhere. And then the lower layer does not make a field, and the composition may vary here from C8, N2, and H19 to H11. That's the lower part, and they have a rocky core here as a result. And then we have a similar model here for Neptune. We have a little bit larger core. The planet is a little bit smaller, but I can assure you that under these assumptions, if you have a rotating planet, everything is in hydrostatic equilibrium, the gravity field will match the existing observations. So we've done now, this is a full description of these models. I want to walk you through a little bit what we're saying, that the phase separation is complete. The hydrogen water layer will is homogeneous and convecting. That's where the field is generated. Then we have the other layer that is stably stratified because the hydrogen composition is changing with depth, and the hydrogen was released and absorbed in this water layer. That's at least something that works at the moment. We're not sure whether it's the ultimate model for the interior, but it has this two-layer structure, and it's compatible with the non-dipolar magnetic fields. So I've done, this is a plot here for the calculations for an ensemble. We're doing this with quadratic Monte Carlo simulations to generate these models. You can read about that here. And the resulting clouds of ensembles basically lead to J4 and J6 that are compatible with the measurements. We also need to make sure that this boundary here is actually stable. So therefore, the density of the lower layer needs to be higher than that of the upper layer. That's why we need hydrogen to be reabsorbed in the water layer. And that's one condition we probe for. And if this is violated, we remove models from the ensemble. We also need to make sure that this lower layer has released more or at least as much hydrogen as we need in the water layer here. So this is another condition we imply. And then we look at whether this radius here of 2/3 is approximately satisfied. So, and we compare this to the solar abundance of the heavy nuclei, and we find a reasonably good match. So we have here models that are either perfectly matching the 2/3 condition, or it's a little bit different from solar abundances. But this is something that you need to do if you say you have a solar composition planet. Is it compatible with this approximate region? The answer is yes. So we also did conductivity calculations, and we showed that the water-hydrogen mixture is a happy conductor. The fully mixed system is also a good conductor. The highest conductivity we actually get for carbon-nitrogen-hydrogen mixture. So all of those fluids are electrically conducting. Therefore, to come back to Stanley and Bloxham's questions, we agree with the hypothesis that the magnetic field is primarily generated in the outer layer. There we have a homogeneous electrically conducting fluid, and then the inner outer radius is 2/3. We agree with the prediction that both of those layers are actually fluid. But now we can actually put some explanation behind it. We think the upper layer is a conducting mixture of hydrogen and water, and the hydrogen comes from the release of the lower layer that is carbon, nitrogen, and hydrogen, but the hydrogen contents is varying, and therefore it can no longer convect. So that's our prediction, what might be happening in the interior of Uranus and Neptune. Hopefully someone will probe this better than gravity, and therefore we propose normal modes should be measured for Uranus and Neptune, and the mission that flies should be a Doppler imager. But I'm told this is an expensive, very heavy instrument, so I'm not sure it will be flown, but I am advocating for it nevertheless. We look for P modes, for example, these modes here shown here. We have general P modes, F modes, and G modes you contribute. And the G modes can only be generated if there is stable stratification. So therefore, if you have stable stratification is basically proposed for Saturn by Jim Fuller. But nevertheless, for G modes to be present, you need a stably stratified fluid. So if you directly or indirectly infer their presence, you can actually say that the lower layer is stably stratified. So the takeaway points from this talk today is that the ab initio simulations predict a homogeneous mixture of carbon, nitrogen, and oxygen. Hydrogen will phase separate into oxygen-rich and the carbon-nitrogen-rich fluids at high pressure. Hopefully, there will be experiments to confirm this. And then that gives rise to Uranus and Neptune interior models that have two layers. The upper one is hydrogen and water-rich, and then the lower one is stably stratified of carbon, nitrogen, and hydrogen. And these things are basically compatible with existing magnetic fields measurements and gravity measurements. But to really probe this, we should actually measure normal modes for Uranus and Neptune. So thank you very much. this is where I want to complete my talk. Thank you.
Wow, thank you very much, Burkhard, for that incredibly complete explanation of your recent exciting results. If you have any questions for Burkhard, then please raise your hand, or you could type your question in the chat.
Are we still recording this question session, or do you stop this, or how do you handle
I can
it?
stop it if you like.
I think it's fine. Sometimes we stop it. I don't know. It depends on how you normally do it.
Okay, well, we generally don't, but I can.
Okay, go ahead.
Okay. I'm not seeing. Can you say a little bit more, Burkhard, about how you are able to separate out the enthalpy and the entropy contributions when you do your thermodynamic integration?
So this is for the composition for the systems that have, for the planetary ices, we've not done this. So this is still on our plate to do. And we've done it very carefully for hydrogen and helium. In general, what you do is we calculate the simulations at constant volume and temperature, and we calculate a free energy.
Right.
So you have a Helmholtz free energy, gives you the F. And at the same time, if you just do regular simulation in the same volume at the same temperature, it already gives you the internal energy, and it gives you the pressure. So if you just run MD, you get internal energy and pressure, nothing special. But now we have the F in addition to this. So for the F, free energy, we add PV. That gives us the full Gibbs free energy. And then we have Gibbs free energy as a function of pressure and temperature. That's one crucial variable to have. And then the entropy we actually get from F equals E minus TS. So since we have the F and we have the internal energy,
Okay.
we get the entropy that way. And then we have a grid for different conditions. And we have every point we get the entropy. And then we just say, what is the curve of constant entropy? And that we just draw by interpolation. So this is normally how we do that.
Yeah. Okay. How is it possible to sort out the exact sort of molecular identity of that carbon nitrogen layer?
Yes, the challenge here is you have 4 elements. I find hydrogen and helium with 2 elements hard enough already. So with 4 elements, the challenge, first of all, is what do you start with? So our assumption is that you have carbon, nitrogen, oxygen in solar abundance. We don't have to do this. You can just assume something else. That's at least a good starting point. And then the question is how much hydrogen you have there. So then you have your starting composition. And the challenge right there is to find a way that to show that its Gibbs free energy is unstable compared to something else. And that's not a trivial calculation. So this is sort of when you do it thermodynamically, you have to know which phases form from which phases, which is not a simple thing. If you have solid materials, then you may have a simple way of knowing what phases are present, but with these, we're struggling with this at the moment. It's not a complete system. That's why we have these simplified assumptions right now. But seriously, if you want to do Gibbs free energy calculations, you have to know what phases are present. Otherwise, you get a lot of garbage. And we've gotten a lot of garbage, I can assure you that, yes.
Yeah. So oh, go ahead. Sorry,
Yeah,
Rob,
this is
go ahead.
Ron. Sorry. Yeah, no, I just want to be clear. So you're saying that the shell of that's making the magnetic field is the water and hydrogen and above,
Yes.
and then the part in your diagram that's orange, is that solid or is that viscous or non-conducting? What's the?
Yeah, so let me just go show that slide again.
Okay, sorry.
So statistics here before it's all. So it's driven by a way to make the thermodynamic driven by the fact that you want to explain the magnetic field. If you want to change any of those two assumptions, you get a different model. But let me walk you.
Yeah, I understand the phase diagram. I'm just not clear on the
Yes.
properties part. Sorry.
So we have the outer hydrogen helium layer that does nothing. So then we say it's fully separated where we have two fluid layers. So both of those are fluid. So this is water and hydrogen here, and that's fully convective. If this is stably stratified, then you wouldn't get any field, any dipolar field. So therefore, this has to convect. So this is convection implies a homogeneous model, and that is water rich. And then below, basically, it is liquid. And as a result, we don't want this to be convective. Otherwise, you presumably get a dipolar field. We need some way to stop convection below. And therefore, we're invoking this concept that you release hydrogen by making polymers. And this process, there are longer polymers down here, more hydrogen released, and there are shorter polymers and less hydrogen released up here. This has a lower density here and a higher density here. Everything is electrically conducting, but the composition is varying, and therefore it cannot convect. So a way to stop convection is hydrogen release here. And that's why we explain that is the argument for a stable stratification. So the alternative way with Lars Stigsrud and other people basically say, or Ronald Redmer said, this is layer here is superionic water, and it cannot convect because it behaves like a solid. The problem with that explanation is that superionic water is a very, very soft material and will be happily convecting. If it happily convects, it will make a magnetic field, and therefore then the whole planet would make a dipolar field. So we don't want this to happen, therefore we invoke this other mechanism. So this is where this all comes from. Does that address your questions, Ron?
Yeah, but I'm still not totally sure because even in your orange region, I mean, is it for sure that the hydrogen is not mobile?
The hydrogen is mobile.
Okay, so if hydrogen's moving, I call it convection, but whatever. If it's possible to transport heat by the hydrogen motion, then couldn't that just like your superionic water that you just mentioned, couldn't it behave the same way, that it would contribute to the magnetic field or not?
Yeah, so Ron, I don't want to advocate this is the only and ultimate model for the unison. That would be a little far-fetched. So just maybe you have interesting ways and new concepts to do. Maybe you want to think about it, make a different model. But basically, how about you come from our perspective? You basically say, I'm looking for a mechanism to have a fluid that is not convecting below here. What could stop convection? And the way what we came up with is basically saying, if the hydrogen contents is not the same, then it will, that is the compositional gradient that is that will stop convecting. If you go diving in the ocean and the salt layers, you have these salt staircases. There are examples for this. This is one way. A compositional gradient is one way to stop convecting. That's the way we put this together.
The other question is related. Well, maybe it's more about the phase diagram. So in your orange region, I mean, are there discontinuities then predicted, or you think it's just a gradient in properties as you go down?
So this is, again, this is a modeling assumption that is not 100% supported by direct numerical simulations. So we just, at this moment, said we just assume there's a gradient in hydrogen, and then for every gradient we go to for every composition we assume. We actually did simulations for this composition at this pressure and temperature, and then and third, what the density is. So that calculation is done relatively carefully. But whether this is age 19 or age 25, or even the carbon and nitrogen are not exactly in these proportions, this is assumed. So are you
and
asking?
then, yeah. Okay, I got it. And then the helium, is it just all in the top layer, or is there helium throughout?
Yeah, so that's two things. We did assume, so first of all, for full explanation, if you just have no excess hydrogen here, then the water will be heavier than the carbon and nitrogen. So therefore, we did need some hydrogen being absorbed from this lower layer. And then the question is, did all of that was released absorbed here? It's possible, but you also get some models, or a good fraction of the models, where some hydrogen actually went up here, and you just have a little bit of excess hydrogen. But you need some hydrogen here, otherwise water's too heavy, and it will actually sink back down.
Yeah, I was asking about helium. Helium. Is all the helium in the top, or is there helium?
Yes, that's currently assumed. Yes. But that's another modeling assumption. I'm happy to make another model, but I wouldn't know of a mechanism to deliver helium with the ices. So yes, but that's something we didn't even consider. Correct. But I'm sure if you put helium in here, it would probably be mixed, but we didn't have any need immediately to do that.
And so this is consistent with what's thought of as the bulk composition?
So, well, compatible. See, one has to dig carefully, and it's consistent with when we assume the hydrogen up here is, this layer is modeled in a typically solar hydrogen helium calculation. And then here we have no helium, and here there's also no helium. You could do this differently. But that's the assumption we've made. I don't think helium plays a crucial role. If you could put it in any of those layers, the models would still work, but it wouldn't be a good discriminator between model A and B, unless you're telling me something I'm not aware
of. Thanks.
On that,
sorry, go ahead.
On that slide, you have some like dashed lines which refer to the superionic transition in H2O. Is that correct?
Yeah, but in pure H2O, you're right.
So like, is that included in the model, or is the entire top layer liquid, or is it?
So yeah, I did not for the models of the planet, it does not matter, because the models of the planet are only used to calculate gravity, and therefore that is not important for whether it's superionic or not. Yes. So, but it's true, if there is no hydrogen dilution, then the water by itself at sufficient depth would become superionic, which would lock the hydrogen atoms in their respective lattice sites. Yes. And whether this is convecting or not is an open question. I think it is convecting because it's just a soft material, but other people may disagree.
But if you have like H5O, then maybe there's like some phase separation between the H2O and the hydrogen or something like that. It's interesting.
Yes, so I think you can look at H3O as the paper with the CDAC paper predicted, or other things. So that is that's still possible. Yes, so all hydrogen and water system is still something that needs to be explored. Yes, I agree.
And for like the second layer with the like CN grouping, when you do simulations of just that by itself, does it diffuse like a liquid at those conditions?
Yes.
Okay.
Eventually it will not, but basically if you have a sufficient fraction of hydrogen in it, it remains diffusive. If the polymers become super long, then that may be limited diffusion, but we did not see any simulations of a solid of H3 and 4, but the simulations, the way we investigate, at least you start with a fluid, you stick with a fluid phase, but it doesn't have to be. For example, you can argue that all hydrogen deep down will be released and you end up with a solid layer. That's also something that could be investigated more. So all these ice systems, we have a plausible explanation, but it may not be the only explanation.
Yeah, great. Thank you.
Okay, Burkhard, we have one more question from Javier Montoya. Thank you for your nice presentation. I would like to understand better how the phase separation ML simulation is representative of the PT conditions ranging from R equals 0.16 to R equals 0.82.
So that is sort of, to publish the first paper, you're allowed to cut a few corners. So if you do a second, third, or fifth paper, you have to be a little bit more careful. So basically, what we've done here is we showed that there is phase separation. And that was the bulk of this first paper that was published in PNAS like 2 months ago. And then we make some simplifying assumptions that now we probably need to go back and do more carefully in follow-up papers. But yes, did we really investigate carefully that the phase separation is occurring under these conditions that exactly match the radius conditions you're asking? The answer is no. We found it where the existing adiabats that were published, on those adiabats, we find the phase separation. And we said, hooray, we ran with it. We make these models under positional assumptions. We assume there's complete phase separation. There's not a single oxygen atom in the lower layer, which is probably wrong, which is most likely wrong. But maybe, Javier, how about you redo this and do this more carefully? So we just had the first paper where we did the phase separation was reported for the first time, and we made a working planetary model. Whether this is the last planetary model, the answer is surely no. But yes, so how about you read the paper and you identify all the little construction sites where you just glance over these things and you write another paper. So,
can I ask another question?
Sure, go ahead.
Okay, so just in terms of the dynamo modeling, I mean, if you had two convecting layers, does that give you a dipolar field too?
No, the assumption is.
No, I understand your model, but if you did have two convecting layers that were convecting separately, would that still give you a dipolar field?
So this, I would say the answer is yes. It would make a dipolar field because there's enough of an ordering force that all the whatever different dipole fields order into one giant dipole. But this is someone like me who has never done a single dynamo calculations in my life, which basically should take anything I say with a grain of salt. It's probably should talk to someone like who does these things. But then you get answers like that this is an open question. I don't want to basically answer this with authority, which I do not have. I assume the tricky part is to not make a dipole field. And a good way to not make a dipole field is a stably stratified lower layer. But if you ask a dynamo people like Hao Kao or Polar Wolf, they now have other ways of making non-dipolar fields. And they not fully agree whether my solution or personally is the only solution. But I hope it's one. I hope it's a good one.
Okay. Well, if there are no further questions out there, then please everyone join me in thanking Burkhard for a terrific presentation, a really delightful talk. Thank you, Burkhard. Vielen Dank.
Okay. Tschüss.
Tschüss.